All right, good morning. This is April the 30th. It's college algebra. This is the last lecture of the semester as we head into final exams. A couple of quick announcements. WebAssign, you have one last homework assignment on WebAssign. It's on nonlinear systems, which is a topic for the final exam. It's not a real lengthy assignment. I believe there's only like maybe 5 or 6 questions on that assignment. That is due May the 8th, which is next Tuesday. It's a week from tomorrow. And remember that I do drop the 4 lowest WebAssign grades at the end of the semester. So that will be a benefit to you. And for some of you, if you've done well on WebAssign during the semester, that grade doesn't affect your final grade at all. Some of you really need that grade. Also remember that, like I said, I drop 4 at the end of the semester. You've got until May the 8th to finish that WebAssign homework note. And it is good review for the final exam on a couple of questions in the final exam. So there is a reason for all of you to do it. So final exam. All right, so a couple of announcements here that are important. I'm going to do an online help session. This is for college algebra students only, so no one else will be online at that time but college algebra students, and that will be Tuesday, May the 1st from 8 to 9:30 p.m. So that's tomorrow night, 8 to 9:30. I will be online, college algebra students only. I will make appointments to meet you in the WebEx office at other times. You just need to email me or send me a remind message, and we can try to set up an appointment at some other times. But I've dedicated that hour and a half tomorrow night only to college algebra students. So don't hesitate to come by if you have questions. The window for taking the exam, the final exams, May the 3rd, this Thursday through Monday, May the 7th. Notice it's Monday, May the 7th. Not Tuesday, but Monday. Take-home problem. Number 14 on the final exam. I'm telling you right now, it's going to be number 14 on the final exam. That problem is going to cover what we cover in class today. And that's a lengthy process. So rather than giving you that problem on the final exam, where you have to take a lot of time to go through that problem, I'm going to give you that problem this week as a take-home problem, and you turn that into me. It will be on using Gaussian elimination and augmented matrices to solve 3x3 linear systems. It sounds real complicated when you say it that way, but you'll see the process today. I will send out that problem tomorrow as an attachment to a remind message. So I will send that out tomorrow. I will probably also post it in the exam reviews on my Google site, just so that you have a second copy of that somewhere if you need it. So I'll send that problem out to you tomorrow. It will be due by be due by midnight, May the 7th, the last day for taking the final exam also. My recommendation would just be to get it done quickly, get it done in the next couple days after I've sent it out, so that you have a chance to work on it and get it taken care of. It is a 5-point problem. I didn't write that on here anywhere, but it is a 5-point problem. All right, so when you hit problem 14, when you're taking the final exam, you will have already finished it, or you'll finish it later in the day. I'm hoping you will have already finished it rather than waiting until after you've taken the final. But it'll be a one-sheet thing. And what I want you to do is I want you to make a PDF copy of that. You could use your cell phone as a scanner with no problem. There's lots of free apps for making your cell phone a scanner, and you can turn it into a PDF. And then what you're going to do is you're going to upload it to my Dropbox. I'm going to send you a file request. I will do that tomorrow also. And when I send you that file request, there will be a link on there. When you go to that link, it'll give you the directions on how to upload that to my Dropbox. So you just upload it to my Dropbox. It's not a big, it's easy, very easy to do. You do not need a Dropbox account to do that. You do not need a Google account to do that. You just upload it directly to that folder, and then I'll have it directly that way. So you will get that link tomorrow also, like I said. So tomorrow, be looking for the actual take-home problem. Also be looking for the link to my Dropbox where you're going to actually deposit that. And remember, that is due by midnight on May the 7th. Today we are going to cover this last topic on solving systems using matrices and Gaussian elimination that we kind of started talking about last week. So before I get started with that, are there any questions from any of you guys that are with me online right now, live?
I'm good. I just came in. I don't know what's happening.
Well, Jennifer, you heard the part on the take-home problem. I'm sending a take-home problem out, and so I'll send that out tomorrow by remind. And that problem is one of the problems on your final exam. So you'll get that problem. You'll get instructions on how to upload it to my Dropbox account. So that's what we're talking about.
Where are we getting it again?
It's going to be on Remind. I'm going to send that to you on Remind tomorrow.
Okay.
All right, so you'll get 2 Remind messages tomorrow, one with the take-home problem, one with the link to my Dropbox. And when you click on that link, it'll tell you what to do to upload it to my Dropbox. Very simple to do. My calculus students do that all the time. It is not a problem at all. It's very easy to do. All right, so then let's go ahead and get started. Last time I did give you some homework on what we've done so far with matrices. And so what I'm going to do now is I'm going to actually work through some of that homework as a review to get us started with talking about using matrices to solve the 3x3 system, 3x3 linear systems. Please don't hesitate to stop me as we go through this if you have a question about something. All right, so the first problem said write the augmented matrix for that system right there. And so remember what the augmented matrix is. We did talk about this in lecture last time. You simply write down the coefficients of the variables. So the first equation is 2x plus 3y minus 4z. So we write 2, 3, negative 4 for the x, y, and z. And then the constant goes on the other side of that vertical dashed line. And so that's my first row is 2, 3, 4, negative 1. And notice that simply comes from the first equation of the matrix. Right? And then you just keep on going. The second equation is x minus y. Notice there is no z equals 8. And so the coefficients then would be 1, negative 1, 0, because there is no z, and 8. And so that would be my second row right there. That second row comes from that second equation.
So I have a question on that one.
Okay.
Why is x? How did you get to the point of x and y being 1 and minus 1?
Look at the coefficients in that middle equation, Anne-Marie. The middle equation is
coefficients. Okay, yep. I was trying to solve for the y.
No.
8. Sorry.
No, it's just the coefficients of each variable is what you're talking about there. Yep. So it's literally the constant that's in front of each variable. All right, and then let's see. The last row, 3x plus 5y minus 6z equals 4. So that would be 3, 5, negative 6, 4. And that would be the last row right there. That's the last equation right there. All right, so for any of you guys that are with me live right now, any questions about how you just write down the matrix, first of all? Everybody's okay?
I'm good.
All right. So now the idea, remember, is what we're going to try to do is we're going to try to take a matrix, or we take a system, we write it as a matrix, and then the idea is going to be to try to rewrite that matrix in what we call triangular form. Now on the next page, we have a matrix that is in triangular form. Right here, it's in triangular form because there are zeros in these 3 positions right here. It's always these 3 positions. And because we have those zeros right there, if you look at the corresponding system that this represents, that last row represents z equals negative 4. The middle row represents y plus 6z equals 8. And then the first row represents the equation x plus 3y minus 6z equals 4, like that. So that's a matrix that's in triangular form, and the system that you get is a system that you can easily solve the system, because the last equation gives you z equals negative 4, and then the middle equation, y plus 6z equals 8. Now that you have z equals negative 4, you can find y. We put negative 4 in for z, we get y minus 24 equals 8. We get y equals 32. And now that we have y and z, the first equation gives us x, right? So we take that z value that we had, and now this new y value that we just found, we put those into that equation, and we can find x. So you have x plus 3 times 32 minus 6 times negative 4 equals 4. So you have x plus 96 plus 24 equals 4. So you have x plus 120 equals 4, or x equals negative 116. And so you get the ordered triple solution, negative 116, 32, negative 4, like that. Right? This process is called back substitution. And you can use back substitution once you've got the system in, or the matrix in triangular form. Right? Because when you get it in triangular form, when you get the zeros in those three positions, you will always be able to use back substitution to solve the system from there. Because you can find z, and then you can find y, and then you can find x. All right, so the idea is, so flipping back now, the idea is, how do we take a matrix like the original one at the top and rewrite it in triangular form? Because notice that matrix is not in triangular form. And you do that by using what we call row operations. And the row operations, I've got 3 problems here that illustrate the 3 row operations, and we did these 3 row operations at the end of lecture from last week. So I want to walk through each one of these row operations again, and then we're going to actually turn our attention to some problems. First row operation is you're always allowed to interchange rows, and that's what we're doing right here, is we're interchanging rows. And notice that I give little instructions there, and this is what I would want you to do, is I'd want you to tell me what you're doing with that row operation. And when I write R1 with a double-ended arrow and R2, I'm telling you I'm interchanging rows 1 and 2. And literally that's all you're doing. Row 2 becomes row 1. Right? So notice I put row 2 in place of row 1. I put row 1 in place of row 2. Row 3 just stays where it is. By the way, a reason why you might want to do that, just interchange rows, is that it is good. It's not mandatory, but it is to your advantage to have this first entry in the matrix be a positive 1. So if it's not a positive 1, but you can interchange rows to make it a positive 1, then that's worthwhile doing. And so notice that I had a 3 in that first entry, first row, first column. And 3 is okay, but it's a heck of a lot easier if I put a 1 there. And so notice I did have a 1 below, so it's nice to just flip rows 1 and 2, and now I've got a 1 as that first entry. Right, so flipping rows is sometimes advantageous, and you can always do that. That's what we're saying here.
And you can flip any rows?
Yes, absolutely. It doesn't matter which rows you flip at all. So when I say interchange rows, any 2 rows would always be a legal move to make. Absolutely. All right, another row operation is that you're always allowed to take any old row and just multiply all the entries in that row by a constant. That's always a legal thing to do. So multiply any row by any non-zero constant. You're not allowed to do it with 0. So just as an example here, not for any particular reason, but just to show you that this is what I'm talking about. The instructions I'm saying here is I'm going to take 2 times row 3, and I'm going to put it in place of the current row 3. All that's just a fancy way of saying I'm taking row 3 and I'm multiplying every entry by 2. So all the other entries, you don't mess with them. None of those get touched. But row 3, I'm multiplying all those entries by 2. So -2, 6, 8, -4. Notice you have to multiply every entry in that row by that constant. You can't just get by with multiplying some of them by a constant. It has to be every entry when you do that. So that's a legal move. And by the way, one reason why that could be an advantage is you might have wanted this number right here to be a multiple of that first one. And now it's a multiple. Originally it was not a multiple. There was no nice whole number or integer that I could multiply by 2 and get -1. I could use a fraction, but there was no whole number or integer I could use to multiply by 2 to get -1. Now there is. And so making it a multiple sometimes can be an advantage like that. So there's a reason why you might want to take a row and multiply it by a constant. So somewhere along the line, you're working through a problem. You go, man, this entry right here is a 3, but I sure would like it to be a 12. It would be a lot easier if that was a 12. Well, then multiply every entry in that row by 4, and then you can make it into a 12. All right, this last row operation is the trickiest one, and it's the one that we use the most often. And this is one where we multiply, I'm sorry, let me rephrase that. We replace, that's better, any row with with the sum of itself and a multiple of another row. Now that sounds complicated, but if you look at the arithmetic, there's a lot of arithmetic involved, but it's not that hard to do. So follow the instructions that I've written right here. Notice what I'm going to do. Notice what row is getting replaced here. The row that's getting replaced is row 2. That's the one at the end. And what am I doing? I'm taking row 2 and adding it to -3 times row 1. In other words, I'm taking a multiple of row 1 and I'm adding it to row 2. I'm putting it in place of row 2. Row 2 is the one that's changing. So row 2 is changing. That's the one right there. The other rows don't change in this row operation. It's just row 2. So I could write down rows 1 and 3. Notice I wrote down rows 1 and 3 first because those don't change in this row operation. But what I'm doing is I'm taking row 2, what I'm replacing it with is I'm taking -3 times row 1 and I'm adding it to row 2. So you're literally taking, let's see, let's do this in a different color here. I'm taking -3 times every one of these entries in row 1. And what am I going to do with that multiplication? I'm going to add it to what's in row 2. All right, so when you do that, the first one, you have -3 times 1 is -3, and you're adding it to what's in row 2, which is 3, and you get 0. And notice that's why you would want to do that. You want a 0 in that entry, and so that's a good move to make there. Then you have to do the same thing with every other entry. So -3 times -2 is +6. You add that to the entry in row 2, which is 2, and you get 8. -3 times 3 is -9. You add that to what's in row 2, which is -1, and you get -10. And then the last entry, -3 times -5, is +15. You're adding it to 4, and you get +19. And that's our new row 2 right there. That's kind of sort of the critical step, is that particular row operation. And we are going to go through that row operation over and over and over again over the next couple of problems. So you're going to see that lots of examples of that row operation over the next few problems. All right. So don't hesitate to shout out if you have a question as we go through this, okay? All right, so I'm not hearing anything right now. So
can you multiply it by any number, or does it have to be the same, a constant isn't a 0?
You can multiply by any number you want. You'll just have to change that by, there'll be a specific number that you will want to use in any given step, and we'll talk about how you're going to figure out what number to multiply by in a minute. I told you -3 in this problem, but that's going to change from problem to problem. It's going to depend on what constants you have in the problem. And you'll see, Anne-Marie, the trick here is you wanted to get this 0 right here. That was key. And so what would I multiply by this 1 so that I got, when I added it to 3, I got a 0, right? I want to get a 0 there. And okay. Does that make sense?
Yes, sir.
Okay. And that's the critical question. That's the question to ask, absolutely. So, all right. So let's see. Now, this last problem in the homework, I actually give you a problem to solve. And notice the direction. Solve the following system using Gaussian elimination to rewrite the associated augmented matrix in triangular form, and then using back substitution to find the solution. That's what we want to do. We want to take a matrix like I've got right here. I'm sorry, a 3x3 system. Write down the matrix for this system, and then somehow figure out how to take that matrix and write it in triangular form, and then solve the resulting system. That's our whole process. This problem I'm going to leave blank because this is a practice problem for you. I want you to look at this one. So I've got some problems written down though, and so that's what we're going to do, is we're going to practice this process. All right, so the problem starts like this. You start with the matrix, or I'm sorry, you start with the system, you write down the matrix that's associated with it. And so notice I just use the coefficients, and make sure I put that vertical dashed line there to separate the constants from the variables. And that's the matrix right there. And so the whole deal is I want to write this in triangular form. So we want to rewrite matrix in triangular form. Now in triangular form, what that means is we want these entries that I'm highlighting right here, we want those 3 entries right there to be zeros. We need zeros in those 3 spots. And what we're going to do is we're going to always, always, always do this in the same order. We're going to get a 0 in that first entry of the second row. We're going to do that one first. We're going to do the first entry of the third row. We're going to do that one second. And then we're going to do this one third. Always in that order. Don't ever deviate from that order. Always first, second, and third like that. All right, so what we're going to do is we're going to use row 1. Use row 1 to get the first 2 zeros. Use row 2 to get the third 0. And you'll see how that works as we go through this. All right, so what we want to do, so I've got a bunch of stuff written there, so what I'm going to do is I'm going to start again right here. And by the way, you want to leave yourself some room here because these problems can take some space. And also, this puts a premium on neatness. And some of you are not especially, that's not your strength, let's just put it that way. And so you want things lined up in rows and columns. You want the columns lined up appropriately. All right, so I need a 0 where that 2 is that starts off the second row. And so I need a number that I'm going to multiply by this first entry right here so that I get a 0 right there when I add it. So for those of you who are with me, you 4 guys that are with me live right now, what would I multiply by 1 so that when I added it to the 2, I got a 0?
-2.
-2. There you go. That's right. And so that's your multiple. So you're going to take -2 times row 1, and you're going to add it to row 2, and you're going to put that in place of row 2. That's going to be your first step right there. All right, so I'm going to write down the new matrix right here. The first entry does not change. So 1, -1, 1, and 8. I'll put in that vertical line like that. The last row does not change. I usually write those rows down first so that I'm not tempted to try to change either one of those. The only row that changes in this case is row 2. It changes. And so as you go through here, you're going to see me changing this row right here. What am I going to do here? I'm going to take -2 times every entry in row 1, and I'm going to add it to the entry that's in row 2. Now I'm going to write that down on this first step, but I'm going to tend to stop writing that because it gets really kind of messy if you write that down every time like that. So it gets, I try to avoid it being too messy. But you're taking -2 times every one of these rows, every one of these entries in row 1. And then you're going to add it to what's in row 2. Every time you're going to add it to what's in row 2. All right, so -2 times 1 is -2. Add it to 2 and you get 0. Yeah, so that's what I wanted. -2 times -1 is 2. You add it to 3 and you get 5. So put a 5 right there. -2 times 1 is -2. Add it to -1 and you get -3. And then -2 times 8 is -16. Add it to 2 and you get -18. And that's our new row 2 right there. Right, that's the one that changed under this row operation right here. All right, and again, please shout out if you have any questions about anything here. All right, so the next step, the second step, is we need a 0 in this entry right here where the 3 is. And so what we're doing here is we are saying, what do I multiply by this first entry? Remember, we're going to use row 1 again so that when I add it to the 3, I get a 0 in that spot right there. That's the spot I'm concentrating on. So what multiple are we talking about here?
-3.
-3, that's right. -3 times 1 is -3. Added to 3 would give you 0. So this is -3 times row 1. We're going to add it to row 3, and we're going to put it in place of row 3. That's our job for this next step right here. So I'm going to write down the matrix. Put that vertical dashed line in there. And then I go through and do the multiplication, right? So this is going to be -3 times this entry, -3 times this one, -3 times this one, -3 times this one, like that. So -3 times 1 is -3. Added to 3. Oh, wait a minute. One thing I forgot to do here. Rows 1 and rows 2 don't change under this row operation. Just row 3 changes. So I write down rows 1 and 2 just like they are. And then I write down the new row 3 right here. Row 3 is the one that's changing in this step. So highlighting that, row 3 is changing. Here's row 3. This is going to be our new row 3 right here. So negative 3 times 1 is negative 3. Added to 3, you get 0. Good, that's what I wanted. Negative 3 times negative 1 is 3. Added to negative 2, and you get 1. Negative 3 times 1 is negative 3. Added to negative 9, and you get negative 12. And then negative 3 times 8 is negative 24. Added to 9, and you get negative 15. The problem here is you make one arithmetic mistake throughout any of this, and you're dead. The whole process is over with. By the way, let me hold on real quick. I just needed to open the door there. So, all right, so you make one simple arithmetic mistake, and the whole problem has been messed up. So you have to be careful about that. All right, so I've got the first 2 entries, right? And so the third entry now, the third 0 I need is in this place where the 1 is. That's where I need this last 0, where that 1 is right there. But now I don't use row 1 anymore. If I try to use row 1, I will lose the 0 at the very beginning of that last row. I need to preserve that first 0 in that third row there. And so I cannot use row 1 in this step. If you do that, you're dead, because you're going to always lose the 0 that leads off that row, and then you will not get the matrix in triangular form. So now I need that, where I'm pointing to that 1 right there, I need that number to be a multiple of the number above it. 1 is not a multiple of 5, because I can't multiply 5 by an integer and get 1. The only thing I can multiply by 5 to get a 1 is a fraction. I don't want to use fractions here. So this is a place where if I want the 1 to be a multiple, I want this entry to be a multiple of the entry from row 2 above it. And it's not right now. So what I'm going to do in this step is I am going to just multiply row 3 by a constant. And in this case, to make it a multiple of 5, all I really need to do is multiply it by negative 5. And I'm going to multiply it by negative 5 so that the sign is opposite. So I'm going to take negative 5 times row 3, and I'm going to put it in place of row 3. It's all I'm doing here is multiplying row 3 by a constant. And the only reason I'm doing that is to make that entry a multiple of the 1 above it. So rows 1 and 2 do not change in this step. The only row that changes is row 3. I multiply every entry by negative 5. Sometimes the numbers on this can end up being a little bit big. And by the way, some of these solutions can be fractions with no problem. The solutions to these can be fractions, messy fractions, in fact. I'm going to basically steer clear of fractions as solutions, including the take-home problem that I'm going to assign you tomorrow. I'm going to, because I don't want you to get hung up in the fraction arithmetic. I want you to learn the process and not have to focus on the fraction arithmetic as you go through this. And so I'm going to avoid gross, messy solutions, not only in the practice problems we're looking at here, but also in the take-home problem. Now, I didn't say that I'm going to avoid big numbers. So the numbers could end up getting big in the middle of the problem, but everything will always turn out nice at the end. If it doesn't turn out nice, then you've done something wrong. All right, and so now notice what I've got here is I've got a situation where I can take a multiple of row 2 and add it to row 3, and I can get a 0 right there. And the multiple in this case is simply 1. If I take row 2 and I multiply it by 1 and I add it to row 3, I'm going to get a 0 in that entry. And that's what I was looking for. And so what I'm going to do is I'm going to take 1 times row 2. I'm going to add it to row 3. I'm going to put it in place of row 3. Now you'll see why that works here as we go through this. So row 1, oh, and by the way, let me, this is I've been highlighting the row that changes in each step. So there's the row that changed in that step. This last step, again, row 3 is the one that's going to change. So you have 1, -1, 1, and 8 is row 1. By the way, if you work through the process like I'm outlining it here, row 1 will never change. Row 2, you have 0, 5, -3, -18. And then row 3, what am I doing? I'm just taking 1 times row 1. So I'm literally just taking row 2. I'm sorry, 1 times row 2. I'm literally just taking row 2 and adding it to row 3. So add here and you get 0. Add in the next entry and you get 0. Add here and you get 57. And add -18 and 75, and notice you get 57 there also. And this matrix at the end here is in triangular form. Right, this is what our goal was through this whole process, is to get zeros in these 3 spots, which we have. This matrix is in triangular form. Now, some people will take this further, and if we had time, we might go through this further, and not just get it in triangular form, but then they would also get 1s down the diagonal. So they would want to get all of these entries to be 1s right here. And then actually get 0s in the other entries also. You could continue the process. This actually gets easier. Every step, the arithmetic gets easier because there's more 0s in the matrix. But I'm stopping here at triangular form. All right, so now what we do, notice, is we can now use back substitution to solve this system. And back substitution is not hard once you've got this in triangular form. The last row gives you 57z equals 57. And so notice you can just divide by 57 there and you get z is equal to 1. That's what I'm talking about right there. You can assume, I'm going to make the simplifying statement here, that you can assume that these are always going to divide nicely like this at the end. We're not going to get fractions. Is that true always? No. But the problems I'm going to look at, I'm going to avoid fraction arithmetic. So you have 57z equals 57, you get z equals 1. And then the middle row gives you 5y minus 3z equals -18. So I put z equals 1 in there, and I get 5y minus 3 times 1 equals -18. So 5y minus 3 equals -18. Add 3, you get 5y equals -15. Y is -3. And then I use the first row, the first equation, which is x minus y plus z equals 8. And I plug in z equals 1 and y equals -3. Those both go into that equation right there. So now we take z equals 1, so you have x and y equals -3, and substitute those in. And so you get x plus 3 plus 1 equals 8. I think I did that right. And so you get x equals 4 when you solve that. And so the ordered triple solution I get here is 4, -3, 1. Now you can always check that. You go to the original system and you make sure that when you substitute that in, those values in, that you get all 3 equations are true, make it all true statements. And I'm not going to do that in this, but never a bad idea to check your solutions at the end of the process. Now I've got a lot of mess written on here, a lot of stuff written out. I'm going to streamline this process a little bit. I'm not going to write all this stuff out each time as we go through this process. It'll look a lot cleaner in the next problem. But this is the process that we're going to use for solving these systems. And you can tell it can get to be a little bit messy. But it's going to be a lot cleaner looking in the next problem. So anybody have a question about this problem before I go on to the next one? I am going to work through 3 problems, by the way.
I'm good. I'm good here.
Okay.
I'm good.
All right. All right. Then let's go on to the next problem. Very good. All right, so here's my next system. So the first thing I do is I write down the matrix associated with this. And, you know, I've even had students make mistakes just writing down this matrix because they're not paying attention. And they make a sign mistake. They drop a negative sign or add a negative sign. And obviously then it's wrong after that. There's no way to get the problem right after you do that. All right, so in this matrix, remember what we want to do is we want to get if we can get a 1 in this first entry right here, it would be nice to do. And so I can do that easily here by interchanging rows 1 and 2. So that's our first step. We're going to interchange rows 1 and 2. So I do that. And literally just flip them. All right, so I flipped those two. All right, so now I'm ready to start my getting with zeros. So the first thing I want to do is I want to get a 0 where this 4 is right here. I need a 0 where that 4 is. Right, that's got to be a 0. That's my first step. And so the multiple I'm going to use here to multiply by 1 to add to the 4 is a -4, right? That's my multiple. And so in this problem, I'm going to take -4 times row 1. I'm going to add it to row 2. I'm going to put that in place of row 2. So that's the row that's going to change here is row 2 in this row operation. So I write down rows 1 and 3 because those don't change. Only row 1 changes. I'm sorry, only row 2 changes. All right, so -4 times 1 is -4. I add it to 4 and I get 0. -4 times 2 is -8. I add it to -1 and I get -9. -4 times -1 is 4. I add it to 2, I get 6. And -4 times -1 is 4. I add it to 11 and I get 15. And so there's my new row 2 right there. All right, so again, stop me if you have a question about that. And obviously check my arithmetic as we go through this. All right, so next step, I need a 0 in this entry right here. I need a multiple of row 1 that I can add to get a 0 there. That multiple would be -2 in this case. So I'm going to take -2 times row 1. I'm going to add it to row 3, and I'm going to put it in place of row 3. Right, so the entry or the multiple I'm using here is -2 in this case. In this row operation, only row 3 is changing, not rows 1 or 2. So I would probably write rows 1 and 2 down first. And then write row 3 down because that's the one that's changing. Do that one last. So -2 times 1 is -2. I add it to 2, I get 0. -2 times 2 is -4. Add it to 2, I get -2. -2 times -1 is 2. I add to -3 and I get -1. -2 times -1 is 2. Add it to -1 and I get 1. And so there's my new matrix right there. All right, now the next step is I need a 0 here. The problem is that -2 is not a multiple of -9. I need that -2 to be a multiple of -9. So that's got to be a multiple of -9. So must be a multiple of -9. So I'm just going to multiply row 3 by 9. That will make it a multiple. That's the easiest one. I could use a fraction. I don't want to use fractions. So I'm just going to take 9 times row 3 and put it in place of row 3. And then after this, there'll be one more step, and we will have the matrix in triangular form. So I write down the first 2 rows because those don't change. Row 3 changes. I get 0, negative 18. Oh, and by the way, I'm sorry. I'm going to multiply this by negative 9. That way it's an opposite sign also. Don't have to do that, but it just makes it easier. And so I'm going to multiply by negative 9, so that gives me positive 18 there. Negative 9 times negative 1 is 9, and negative 9 times 1 is negative 9. And there's my new matrix right there. And then finally, I can get multiples here because I can just multiply row 2 by 2 and add it to row 3. Right? I'm just multiplying by 2 here, and then I can get a 0 where I need it. So this is 2 times row 2 added to row 3, and I'm putting that in place of row 3. So row 1 stays like it is. Row 2 stays like it is. Row 3 is the one that's changing. I get a 0. 2 times negative 9 is negative 18. I add it to 18 and I get 0. 2 times 6 is 12. I add it to 9 and I get 21. And 2 times 15 is 30. I add it to negative 9 and I get 21. That matrix is in triangular form. All right, and now I can solve the system. And I've got plenty of room on the side here to do that. We're going to use back substitution right here. And when I use back substitution, the last row is 21z equals 21. So I get z equals 1. You won't always get z equals 1. But I did on this problem, and I think I got that on the last problem also. Middle row is negative 9y plus 6z equals 15. So I substitute z equals 1 in there, and I get negative 9y plus 6 equals 15. Negative 9y equals 9. Y is negative 1. And then finally, the first row is, at the end there, is x plus 2y minus z equals negative 1. So I substitute negative 1 for y and 1 for z. And I get x minus 2 minus 1 equals negative 1. X minus 3 equals negative 1. Add 3 and you get x equals 2. And that would be my ordered triple solution, 2, negative 1, 1. Right, that is the ordered triple that makes all 3 of the original equations a true statement. And always a good idea to actually check that and make sure that that's actually true. To actually take 2, negative 1, 1, substitute it into those first 3 equations and make sure it makes all 3 of them true statements. All right, and so I'm going to try to get this last problem done before I have to leave because I have people making sure my house doesn't burn down. So we're going to work through one more problem here. The matrix here is 2, 1, 0, 2. 1, 1, negative 1, 4, and 3, 2, 1, 0. So one more problem. I want a 0 and a 1 in that first entry. I need to swap out these 2. So I'll swap out rows 1 and 2 here. Makes sense to do that. So I swap out rows 1 and 2. And now I need a multiple of row 1 to multiply to get a 0 there. So that would be negative 2. So negative 2 times row 1 added to row 2. Put that in place of row 2. So 1, 1, negative 1, 4 is row 1. 3, 2, 1, 0 is row 2. And the row is row 3. And so row 2 would be 0. I'm multiplying by negative 2. Negative 2 times 1 is negative 2. Add to 1, you get negative 1. Negative 2 times negative 1 is 2. Add it to 0, I get 2. And negative 2 times 4 is negative 8. Add to 2, and you get negative 6. Now I need a 0 here, so I'm going to multiply by negative 3. So negative 3 times row 1 added to row 3. Put it in place of row 3. So 1, 1, negative 1, and 4. 0, negative 1, 2, negative 6. And then I've got negative 3 times 1 is 3. Added to is negative 3. Add to 3, I get 0. Negative 3 times 1 is negative 3. I add it to 2. Negative 3 times 1 is negative 3. Add it to 2, I get negative 1. Negative 3 times negative 1 is 3. Add to let me make sure I did that right. Negative 3 times 1 is negative 3. Add to 2, I get negative 1. Negative 3 times negative 1 is 3. Add to 1, I get 4. Negative 3 times 4 is negative 12. Add to 0, I get negative 12. And then finally, I need a 0 here, and this is already a multiple, so this works out well. Negative 1 times row 2 added to row 3. I put it in place of row 3. I don't have to do any creating multiples here on this one. This one is okay like it is. All right, so what I need for you to do is see if you can finish this problem here real quick. All right. So we're taking negative 1 times row 1. We're adding it to row 3. I'm sorry, negative 1 times row 2, adding it to row 3. And do you all see that why I had to be negative 1 here is because I needed to get a 0. So the signs have to be opposite. So negative 1 times 0 is 0. Add it to 0, you get 0. Negative 1 times negative 1 is 1. Add it to negative 1, you get 0. Negative 1 times 2 is negative 2. Add it to 4, and you get 2. Negative 1 times negative 6 is 6. Add it to negative 12, and you get negative 6. Like that. And so that's the matrix in triangular form right there. All right, so, and then now that it's in triangular form, we can solve using back substitution. And I actually think I have room at the bottom here. So you get 2z equals negative 6, so z equals negative 3. And on this problem, I think I might actually show the check, just to make sure that everybody knows what I'm talking about. Middle row is negative y plus 2z equals negative 6. So you have negative y plus 2 times negative 3 equals negative 6. Negative y, let's see, minus 6 equals negative 6. Add 6, you get negative y equals 0. So y is 0. Nothing wrong with x, y, or z being 0, by the way. And then the first equation is x plus y minus 2z equals 4. So you get x plus 0 minus 2 times negative 3 equals 4. X plus 6 equals 4, or x equals negative 2. So there's your solution. So you get the ordered triple solution, negative 2, 0, negative 3. Now, Anne-Marie and Charlotte were both working this. So what about you two? Were you in that direction?
On the last question, you say x plus y minus 2z equals 4. Isn't that just negative 1?
Oh, thank you. Yes, absolutely. You are absolutely right.
Yeah.
So thank you. So
no, I was on your path too, Charlotte.
So okay, good. So thank you for bringing that up. So I erased that. So it's x plus y minus z equals 4. That's better, right? And so you get x plus 0 minus negative 3. Okay, I've got to be careful now that I'm doing that correctly, equals 4. All right, and so you have x plus 3 equals 4, or x equals 1. Does that look better?
That's what I got. Yeah.
All right, so let's check that now. So you have 1, 0, negative 3 is the solution. So my first equation, and I'm going to put the check over here in green. So the first equation at the very beginning of the problem is 2x plus y equals 2. So that would be 2 times 1 plus 0 equals 2, or 2 equals 2. Check. So the first one works just fine. Second one is x plus y minus z equals 4. And so you get 1 plus 0 minus negative 3 equals 4. So that's 1 plus 3 equals 4, or 4 equals 4. So I'm doing good. That one works out. By the way, don't think that just because it checks the first equation or the first two equations that it's the solution. You can easily get an ordered pair because there's an infinite number of ordered pairs, or I'm sorry, ordered triples that make the first equation true. There's probably an infinite number of ordered triples that make the first two equations true. But there's only one that makes all three of them true if there is a solution. So this last one would be 3x plus 2y plus z equals 0. So you get 3 times 1 plus 2 times 0 plus negative 3 equals 0. And sure enough, you get 3 plus negative 3 equals 0, or 0 equals 0. Check. So now I know I'm good. That's the ordered triple solution to the system. All right, the last thing to mention here, so that's 3 worked out problems, is if you were to end up with a matrix that looked like this, where you got, and this can happen, where you got all zeros like that on a row. If you get all zeros in a row when you're doing row operations, then this is what we call a dependent system. And there are going to end up being an infinite number of solutions in this case. On the other hand, and by the way, I'm not going to give you a one like that on a test, certainly. If you end up with zeros for the variables and a constant that's not 0, like that for the constant term of that equation, then this is an inconsistent system, and there's no solution to the system. And I just wanted to mention those special cases here. All right, so as I have said, now you've got a problem, a practice problem that you can work that's part of these notes at the beginning of the lecture. It was part of the homework there. That problem is a good practice problem. So you can work that one. There's also a practice problem that's on your exam review. So you have a couple of practice problems that you can look at to work through. And then you are going to have a take-home problem on this material. So I wanted to, so expect the take-home problem. Let's see. So expect the take-home problem to be mailed out tomorrow. Tomorrow by WebAssign, by Remind. I'll send that out. I will also send you out the link to turn in the homework tomorrow also. Link for turning in homework for that take-home problem. Link for turning in take-home. That will also get sent out tomorrow by Remind. Also, don't forget, please don't forget that we have a final exam help session. I'm going to call it formally a help session for Math 13-14 for college algebra. And that will occur tomorrow night, Tuesday, May the 1st. and that will be from 8 to 9:30 p.m. If we have to go later, that's fine. If there's people there who want to ask questions, and we'll keep on working. I don't have a problem with that at all. All right, other times also you can make by appointment. So anybody have questions?
I'm good.
All right, so if there are